Okay, thank you very much, Enyo, and good morning, everybody, for giving me this opportunity to give some updates on the ILL. So I'm Manon Letiche. I'm the scientist representative of the IRT Nanoelec at the ILL, and I'm responsible for TENIS irradiation station. So I will give you some updates on what's going on at ILL. So first, a few key numbers, few reminds. So ILL has been founded in 1967, and it's a research structure operating the most powerful high flux reactor in the world, 58 megawatt, to provide neutrons for research. It's operated with a budget of 100 million euros, mainly provided by the member country, so France, Germany, and the United Kingdom, and other European countries. We have more than 150 scientific experts that can operate around 30 instruments for academic and industrial users. So many of our research is dedicated to fundamental research and 40% for societal challenges. What can we do at IELL? There is several techniques that can be performed. So we can do diffraction to determine the structure arrangement of the atoms in a sample. We can do small angle neutron scattering that provides statistics on the microstructure. We can do neutron reflectometry, which has its counterpart with X-rays, which provides information about interface and surface. We have imaging that provide information on microscopic structure. And we can also do spectroscopy to determine movement of atoms. So now I will quickly speak about the Endurance project, which is a big upgrade that will occur in ILL very soon. So we are starting our second phase this year, so which a very high budget, I would say. And as you can see, around 26 instruments are impacted. Either new instruments are upgraded. On the short scheme on the right, we can see which ones. So there is two main neutron guide. So there is, for example, D10 or D07, which will be upgraded, or there will be new instruments such as SAM, which will be a small angle instrument. My second point on this part is the remote access control. So this thing is mainly due to the pandemic context. So we've put a lot of efforts on Nomad. For those who already know, the ILL Nomad is the interface control between the instrument and the operator. So now we can operate it from, we have remote control to operate instruments. Of course, we still need the scientists to put in place the samples. And we also created Visa, which is a virtual interface where you can collect you have access to your data, and you can perform data reduction or data analysis. You have access to all the homemade or ILL software that we are used to use to reduce our data and for data treatment. So now I will go a bit further and describe for you two of our beamlines. So TENIS, which is the irradiation station that will be operational in 2021. And next the neutron X-ray and tomograph that will be, which is our imaging instrument, and it will be fully ready by 2022. So let's start with TENIS. So why? First, with a bit of context, why irradiation of electronic devices are so important, and why, in particular, thermal neutrons. So if we look at in the space, there is the galactic cosmic radiation and solar energetic particles. So it mainly contains protons and heavy ions. So these particles are trapped in the Van Allen belts and so generate some high energy electrons. And all of this, by interacting with the Earth atmosphere, created a cascade of secondary particles, the so-called air shower. And so, as we can see on the picture on the right, at the high altitude level, we can have protons, heavy ions, and neutrons of high energy mainly and few thermals. And at ground floor, so sea level here, we have mainly thermal neutrons and few high energy neutrons and also alpha particles. So if we focus on thermal neutrons, when we send a thermal neutrons on a boron atom, there is this particular nuclear reaction that's happened. It creates a lithium recoil and a gamma and an alpha particles. And in our current technology, there is in microelectronics, there is some technologies containing boron 10. So these technologies need definitely to be tested with thermal neutrons. And when thermal neutrons interact with the boron 10, it creates what we call a bit flip in the logic system. So we have to draw below. So for example, a 1 becomes a 0, and this is a single event upset. And when there is multiple single event upset, there is several bit flips in the same logic system. So now if we move to irradiation, to the station itself, so it will be available next cycle. So the beam characteristic, this is a fission spectrum, which means that this is no mono-energetic. There is thermal part, so around the milli-electrovolt energies, but there is also epithermal neutrons and few high energy neutrons around 1.5 mega electrovolt neutrons. The size of the beam is 50 by 50 square millimeters, and the flux is really high, 10 to the 9 neutron per square centimeter per second. We can also investigate to perform this station is compatible with total ionizing dose test, because with the neutrons, a high flux of gamma is coming from the reactor. And so the ambient dose is quite low, but still for a background it's really high. And with by capturing the thermal neutron in a cadmium foil, we can generate up to 115 gray per hour, which is already something significant. Now, if I move to the imaging instruments, so first I should say that the next neutron X-ray tomograph, an X-ray tomograph is the first public imaging instrument, and it is and will be even more a world-leading instrument. So this is a collaboration between the ILL, the UGA, and the HZB, so French and German collaboration. And this instrument is able to simultaneously perform X-ray and tomography. So what can we do? We can do 3D attenuation. We can do quantitative geometrical measurements, digital volume correlations by occurring in a short times, multiple series of measurements. And we will go up to the 4D data with the time component. So how it will be? So it will be available in 2022, and there is the imaging as we do today. And soon there will be energy selective imaging, polarized imaging, and grating interferometry. All of these parts are coming from the HZB Berlin, and with a monochromator or polarization optics, we will be able to perform to propose at least a very broad panoply of imaging techniques available in the world on one instrument. Here a few examples. So the first one is fuel cells. So in fuel cells, there is oxygen and hydrogen that are injected to generate electricity, and it creates, as byproduct, having water vapor. So in the image, we can see and localize where the water is. And on the right, we have a new record of acquisition time for fast neutron tomography. As we can see, one radiography was collected in less than 1 second, which was a new record last year, to investigate water infiltration in soil in a living root system. How being able to work and come at high LL. So we can go through public beam time. So we have 2 rounds of call for proposal per year, spring and autumn. So this is a way to get beam time. We can also, for industry, more particularly, have rapid access. We do also technology transfer or via collaborations such as Horizon Europe, the IRT Nanoelec, or PhD. There is many ways to get beam time. So as a conclusion, I would say that the ILL is a world-class institute which has a wide variety of instruments, and we keep pushing back the limit of science. We have a new irradiation station available since now, I would say, and it's fully dedicated to thermal neutron irradiation of electronic components in the framework of the IRT Nanoelec. We have a world-leading imaging instrument, which will be fully upgraded by 2022. And if you want to know more about other instruments that are concerned, you can follow the last link, and you will have found a poster and many information depending on what you are looking for. So thank you for your attention. And you have the question and remarks if you want to leave some questions, and we will have a question and answer at 10:45. And I leave now the floor to Ennio Capria from the ESRF.